Welcome to week 5 and what will be my final video lesson. I'll see you all next week by the sounds of the government announcement. So let's see what we can get done today so that we're back on track in school next week. We're continuing on with coordinate geometry. You can see here that I've already laid out this piece of paper with some notes. I would strongly suggest that you are taking notes during this video. Not sure what exactly all of you have been doing in previous videos, but this one is quite content heavy. There is a lot that we're going to cover. So, to start with, parallel and perpendicular lines. Collinear means that they are on the same line. These are 3 things that you might be asked to prove when you're given a set of coordinates or points on a graph or line segments. So, let's look through this. Parallel lines. We all know that parallel lines should have the same gradient, and they are essentially like train tracks. They never meet. In coordinate geometry, you might be given a set of points. If they're being nice, they may give you the actual line equations. But let's work with just the points. So let's say that we have one line segment in between these 2 points here, negative 5, 3 and 4, 0. Let's say that our second line segment falls between the points 9, 0 and negative 3, negative 2. You might be asked to prove that these lines are or are not parallel. So, if we know that parallel lines should have the same gradient, because they're running along the same path, they have the same slope, we need to actually calculate our gradients. Remember, I generally use m for gradient. That's because in our line equation formats like y equals mx plus c, or y minus y1 equals mx minus x1, m always stands for gradient. I'm saying m1 here because I'm looking at my first line segment. So, using my rise over run or change in rise over change in run that we've done over the last 2 weeks, note that I'm picking y on top, excuse the smudging, and I chose to start with my first point here. 3 minus 0 is of course 3. Negative 5 minus 4, despite the smudging, is negative 9, which leaves me with a final gradient of negative 1/3. Note that I switched where my negative is here. You might have had your negative out the front of the fraction, so it's a negative, then 1/3. You might have had negative 1/3 like I did. You may have kept it as 1 over negative 3. They all mean the same thing. My second gradient. Hopefully, for these to be parallel, this will turn out to be the same gradient. I follow the same procedure, finding my gradient. Note my double negative, be very careful with these. Just like that, which will leave you with 2 over negative 6, which again simplifies to negative 1/3. From this, we can see that our first gradient does equal our second gradient. Just to clarify this a little bit further, I'm not going to go through it in depth, but I will make reference to it as we're going through collinear points. This must also does also have no point of intersection. Might seem too simple or like common sense that you already know, but it might slip your mind as you're working through a task. Parallel lines cannot have a point of intersection because they are removed. They're like those train tracks. But if you're given a set of random coordinates, you might not have actually wondered or thought or checked whether any of those points are on the same line or cross over. So it's just good to check that there is no point of intersection. This could be done by checking that, for example, one of these points here, maybe 4, 0, does not have the gradient of negative a third to get to one of these points, for example, negative 9, 0. Now, of course, if I've gone from negative 9, 0 to negative 4, 0, or 4, 0, sorry, clearly I've not risen at all, so common sense tells me that it couldn't be the same gradient, therefore they are removed from each other. You could always take your graphics calculator and graph the equations of these lines, because remember last week we did come up with different ways to find the line equation. They must have no points of intersection. Okay, perpendicular lines. Perpendicular lines must always intersect at right angles. Exactly the opposite, I guess, to having the same gradient. Note that this line here has essentially been pivoted, rotated from the y-axis, which also means that this line has been rotated from the x-axis, but they've been rotated by the same amount. These equations, just for the purposes of this example, might be, just looking at it visually and making an estimate, might be something like 2x minus 1 for this equation here. Looks rather steep, so gradient of greater than 1, and it crosses below the x-axis. My second equation might be something along the lines of negative a half x plus 1. Let me run you through why I chose those gradients. They are indeed perpendicular, and we're going to come up with a proof for that soon. Note my comment just before about how each of these lines has been rotated. We know that the x and y axis are perpendicular to each other. They meet at right angles. So if I rotate or spin those a certain amount, clockwise or anti-clockwise, that right angle will be retained. That means if I have a rise of 2 and a cross by 1, because this gradient is 2 or 2 over 1, then the opposite thing must have happened to my second line. Rather than a rise of 2, run of 1, we switch that around. Rise of 1, run of 2. My second gradient has that. But of course, because they are perpendicular, we can see that 1 is positive, 1 is negative, which is why I have my negative here. So in terms of my rotation, I shifted it up. But when I'm looking at the actual calculation of gradient, of course, moving from left to right, I have my negative. So I can tell that these two equations, or these two gradients, are perpendicular. We need a better system rather than having to go through that drawing hassle. If I multiply these gradients together, I'll get my 2 over 1 multiplied by negative 1 over 2, which would equal negative 2 over 2. Remember, we multiply top by top, bottom by bottom. That simplifies to negative 1. Every single time you have perpendicular lines, those two gradients, whatever you call them, will multiply to negative 1. If they do not multiply to negative 1, They simply aren't perpendicular. They are the negative reciprocal of each other. All right. Collinear. Funny word, but co means together, linear, line. They're together on the line. You might be given a set of points. I'm using 3 here today, but in a much larger task you could of course be just picking out a few points from a much larger problem. Let's say for this example that these points are -3, -2, 0, 0, and 6, 4. 1, 2, and 3 points. For these to be collinear, they would of course need to appear plotted on the same line. Might be easy to see visually if you've drawn it to scale, but in a rough sketch you may not be entirely sure. And bear in mind at level 2 we are asking you for a mathematical explanation. That does not mean you draw it and see something, it means you have a method to the madness. So, if my 3 points are indeed on the same line, it should mean that all combinations of gradient are equal. That is to say that this gradient here would be equal to this gradient here. And because they are the same, the gradient from A to C would be the same as well. You could choose to check any 2 or all 3 of these points for gradient. I'm just going to do 2 for the sake of time. I suggest that you do the third combination to check that that is also the same while I'm going through this. So I'm going to use 0, 0 as my common point. So though that's not the first one I wrote, I'm going to start with that. And what I'm labelling as M1, my first gradient, is going to be 0 minus -2 over 0 minus -3. So I'm looking at the gradient between these first 2 points here. Naturally that comes out at 2/3, accounting for my 2 negatives on the top and bottom. Now because I said I'm using 0, 0, the origin, as my common point, that's why I wrote it first in my gradient calculation. I'm going to use that again in my second calculation. You could have picked a different 2 here. -3, -2, and 6, 4 together. How about you try that? You can see there from my calculation, of course, -4 over -6 simplifies to 2/3 again. Those negatives cancel out. Hopefully you've tried your third combination here, from the first to the third points, and you've found that the gradient is still 2/3. So, once again, just like with parallel lines, I'm seeing that my 2 gradients, or more, are equal. And that's why I highlighted this point here, this note, that there should be no place of intersection for a parallel line. That's because we see something very similar here. M1 still equals M2 for a collinear set of points, but this time there is intersection. As I write this down, note that I'm using common point as a phrase for intersection. For example, this line here in the positive section intersects with my negative section of the line through the origin. It's just that they intersect in a manner that they blend together. They are the same line. They carry on into each other. They don't pass and cross through. So common points, also known as intersection. Of course, if you're only looking at 3 points, it may occur to you that there's only one point of intersection, that's 0, 0. But really, because they are all the same line, if you found the equation of the line for any combination, it would be identical. In reality, there are infinite points of intersection. From your information that you were given, in terms of coordinates, there may be 1 or 2 or 3. But mathematically, if we look at the nature of our lines, there are infinitely many points of intersection. All right. Those 3 key skills are now done. We can apply that to properties of quadrilaterals and triangles. Before I go over this, I would suggest that if you're not going to re-watch the video, that you pause it here and actually make a copy in your book of all of these shapes. Quadrilaterals, 4-sided shapes, triangles, 3-sided shapes, all types of polygons. In a larger coordinate geometry task, an internal assessment or a practice task, anything like that, you might be looking at some sort of context that has these shapes, or some of them, 1 or 2 of them, as part of the task. We can apply all of these properties and what we've learnt previously to identify which shape we may have. So, let's get started. Hopefully you've copied those down now. This first shape here. All sides are equal in length, that is. All sides, or pairs of opposite sides, are parallel. These two parallel to these two. These two are perpendicular, these two perpendicular. All angles, that is, are right angles. We know this to be a square. So again, I'm going to go through these kind of properties for every shape. All sides are equal, all angles are equal, opposite sides are parallel. When I say that all sides are equal, note that you can test what those lengths are if you have the coordinates by identifying the length, which we did in lesson 1 of coordinate geometry. If you also included the diagonals, you would note that the diagonals are of equal length and that they bisect each other. They cut each other in half, that's what bisection is, at right angles. There is lots to look at in a square. Next one down. Here we see that opposite sides are of equal length. These two longer ones are equal to each other, but are not equal to the shorter ones, which are equal to each other. Angles are all still equal at right angles. We know this to be a rectangle. Note that if we looked at our diagonals now, you would still find that the diagonals are of equal length, but they do not bisect each other at right angles. They will still bisect each other, but it won't be at right angles. Next. Opposite sides are equal, but it does not look the same as a rectangle. That's because these angles are no longer right angles, so I cannot include that there. This is a parallelogram. Watch where you put those L's. Parallelograms, like rectangles, have opposite sides of equal length. Also note that opposite angles are of equal length. Sorry, not length, equals size. But I have to note my other pair of angles separately because these angles are not the same. opposite angles are the same. I needn't worry about my diagonals here unless I want to show that they are not equal. So this diagonal is clearly going to be a lot shorter than my other one. Next, this looks like a square that's been slanted over. Once again, like a parallelogram, opposite angles are equal, not adjacent angles, and not all angles. Just like with a parallelogram, my diagonals cannot be treated the same. This diagonal is going to be shorter than this diagonal here. We know this is a rhombus. Note that with a rhombus, your diagonals will bisect. I didn't draw that very well. So, like a rectangle, they bisect, but it's not at right angles. Because of our slanting, they are not at equal length either. Hopefully you're keeping up with all this. Next, trapezium. Just to keep things clear, since I'm no longer using my dashes to indicate length, because none of these lengths look the same, I'm now slightly more free to use these arrows which indicate parallel. One pair of opposite sides are parallel, just the opposite ones. These two could be anything. They could be on an angle, one could be very long, it doesn't matter. It could be the upright, vertical sides that are the parallel ones if this whole thing was rotated. Remember, all of those things can happen. This is known as a trapezium. One pair of opposite sides are parallel. Here we have almost exactly the same thing, where we have our opposite sides, just one pair of them, are parallel again. However, just making this difference clear, I note that these two sides, the ones that aren't parallel, are the same length. It's still a trapezium, but because we have two sides as the same length, we call this an isosceles trapezium. So to find all of these differences, remember that we have learnt how to calculate length, which can show these are equal. We have just learnt how to prove that something is parallel to another line. Next one down. Here we see that adjacent sides are equal, sides next to one another. There is also one pair of opposite angles that are equal. If we were to look at our diagonals here, which has been irrelevant for the last couple of shapes, I would be able to see that they are not the same length, but they do intersect at 90 degrees, just like we saw back with our square. Oh, actually, while I'm making that note, I think I forgot to note down that the diagonals of a rhombus bisect at 90 degrees as well. I believe I said that. I don't think I made that note, so I've just added that in there. Back to this quadrilateral here. In this particular orientation, this vertical diagonal bisects my horizontal. That's due to the nature of those equal angles. We know this as a kite. Perhaps not a very mathematical name, it would seem, We're not going to go out and fly them today, but yes, it is a kite. Final quadrilateral I'm going to talk about, once again, has adjacent sides equal in length, also has two opposite angles equal. They may not look opposite, but this being angled back in just makes it a concave polygon. Nothing else changes. Of course, our diagonals just don't work here, so we don't need to worry about those. Properties of the kite no longer hold, even though everything else was similar. We know this is an arrowhead. All done for quadrilaterals. Moving on to triangles. Top right here. Clearly, we have a right angle. None of these other lengths appear to be the same, so this is simply a right-angled triangle. You might be required to show that these lengths are all different, perhaps. Although, of course, we could have a right-angled triangle that has a couple of lengths the same. We'll get to that shortly. Remember, right-angled is perpendicular. Second one. These lengths are all the same. These angles are all equal. Must be an equilateral triangle. Now, of course, in coordinate geometry, we haven't focused so much on actually calculating angles. That's something that comes in more in trigonometry, which is an internal we'll do later in the term. But it's still good to note what those properties are. Parallelograms and rhombus, kites, arrowheads, you may not be able to calculate some of these angles, but it's worth knowing the properties. Next one down. I see I have two lengths that are the same, but not the third. That means the two base angles are the same. This is an isosceles triangle. So you could show that two lengths are the same. For an isosceles triangle, this bisector intersects your baseline right in the middle at the midpoint. That's another skill we've done. And it meets it at right angles. Next one. This looks very similar to the first, and indeed it is a right angle triangle with two lines with perpendicular gradients. However, we also see that these lines, these sides, are the same length. So, similar to our trapezium here, this is an isosceles. I think I've lost my ability to spell. Must be time to wrap this video up. An isosceles right-angled triangle. Hopefully that hasn't gone off the screen for you. Final triangle. It has none of these features. None of the side lengths are equal. None of my angles are perpendicular to, or 90 degrees in any corner. I can't really find out much about this at all, but it's still a triangle. Its name is scalene. So, final comment from me. You might be given a task where you have a random assortment of points on a page. Part of a task could always be identify or explain what shape or the properties of the quadrilateral or the properties of the triangle that you have in front of you. So In some cases, simply finding some lengths can tell you almost enough information. But then you might need to prove that two lines are perpendicular to each other, or that something crossing through a midpoint is perpendicular, thereby using all of your previous coordinate geometry skills, midpoint, gradient, distance, coming up with equations of lines, or using parallel, perpendicular and collinear to eventually be able to identify any of these shapes using coordinate geometry methods, not just by drawing it out and going, that looks like a square. Always using coordinate geometry methods. I know we've covered a lot. You've done very well if you've got to the end of the video. Remember, take notes, go back through this. You probably won't be able to mute me so much in this because of all the talking I did here. But please do go back through it or email me if you have any questions. Well done.